Okay, let's talk about reaction rates or rates of reaction. It exists in a field we call chemical kinetics, and that just is how fast does a reaction go. So up until now in Chem 1, all you've been introduced to is the stoichiometrically balanced reaction where some amount of A reacts with some amount of B and it produces product C. But we haven't talked at all about how fast reactions go. Some reactions go very slowly and some reactions are quite fast. So let's just introduce a few of those. So chemical kinetics is the area of chemistry concerned with the speed or the rate at which a reaction occurs. So milk spoiling is a reaction that you're familiar with, and milk can spoil fairly slowly, and it can spoil rather more rapidly. And the condition that you probably experience that determines whether milk spoils fast or slow is whether or not you put it in the refrigerator. You put it in the refrigerator, you keep it cold, it tends to spoil. It will eventually spoil, but it spoils more slowly than if you just leave it out on the kitchen counter. So that's probably your first clue that temperature is going to play an important role in reaction rates. Iron rusting, iron can rust in more rapidly in some environments. The Golden Gate Bridge is a bridge made of iron out in San Francisco, and you actually have to protect the surface of the Golden Gate Bridge by painting it. You paint it every single year to protect the iron itself from the salt air that's surrounding it. So the environment in which iron rusts can determine the rate as well. So what controls the rate of the reaction? Well, concentration controls the rate of the reaction. That is, how many moles of a particular substance do you have confined to a small volume of space, and we refer to that as concentration. The unit of concentration you're most familiar with is molarity, but as you now know, you've got other units like molality and percent by mass, etc., parts per million. Temperature, as we've mentioned, can control the rate of the reaction, and you can think of the velocity or the kinetic energy of the molecules that are in solution. How fast are those molecules moving? And what that enables them to do is to collide in the correct orientation with a sufficient amount of energy to actually react with each other. The presence of a catalyst can speed up a reaction without actually participating in the reaction itself. Or if it does participate in the reaction, it gets returned at the end of the reaction, so the concentration of the catalyst doesn't depreciate over time. The physical state of the substances in a chemical reaction. Are they in a gas state? Are they in a solid state? Or a liquid state? Are they dissolved in solution? So the physical state of the components of the reaction. We will focus principally on concentration and temperature. Our initial foray is going to focus only on concentration, and so you'll hear me refer to reactions taking place at a particular temperature. All right, and so that'll just be a constant for the reaction, and then we will start changing the temperature to examine the effect of the change in temperature on the reaction. So why are some reactions violent and some slow? If we look at the decomposition of something we call TNT, and TNT is just an acronym for trinitrotoluene. This is a high velocity explosive that The military and commercial industry has used in the past. Very powerful stuff, not something that you really want to mess around with. So let's see if this is going to work. It's a video of the decomposition of trinitrotoluene.
Army and civilian scientists test a TNT super explosion in Utah's wastelands. Engineers bury 320,000 pounds of TNT blocks in a carefully charted clay pit. Hundreds of miles of electric cables lead to a heavily armored trailer, one of many underground structures which represent subsurface shelters and factories.
That doesn't look safe.
The final link to the charge, 1/5 the strength of the first atom bomb, is put in the connecting cable. The Warner Pathé News cameras are nearly 4 miles away. The effects of the test are kept secret as the Army evaluates the result of the biggest non-atomic explosion ever made.
So I think the date on that was 1951. As you can tell from the film, announcers, they got pretty crazy and excited. That was the announcing style of the time, and I remember those days. So here is trinitrotoluene. I think it's 2,4,6 trinitrotoluene. If you take organic chemistry, you'll find out why it's called 2,4,6 trinitrotoluene. There are 3 nitro groups on it. But in any case, it decomposes to just a flurry of gases at high velocity, which is what causes the shock wave. Then you have slow reactions. Those of you that thought diamonds are forever, the James Bond novel by Ian Fleming, might be very disappointed to discover that diamonds are actually not forever. They're created in volcanic chimneys in a mineral called kimberlite under high heat, high pressure. And once you remove that heat and pressure, they very, very slowly, over many thousands of years, decompose to graphite. So eventually your diamond engagement ring will wind up being in a pencil lead, which is actually graphite, which is a planar molecule that sloughs around. Both of these are what we call allotropes of carbon, diamond being a 3-dimensional, very strong structure, and graphite being planar. These planar sections are held together by intermolecular forces, and they slough off when you're writing. Let's take a look at one more chemical reaction. This is going to be hydrogen gas and oxygen gas. I think you'll enjoy this foolishness. And here we go.
All right. Here we go. 5, 4, 3, 2, 1. Really? What'd you see?
My ears are ringing like crazy. So are mine. Yeah, I got it.
So there you go. A couple of different reactions demonstrating slow and fast reactions. Actually, the formation of water from hydrogen gas and oxygen gas, technically speaking, it requires a certain amount of activation energy to get to what we call the transition state. So the hydrogen and oxygen gas in the balloon, while they are quite explosive, are quite comfortable to just hang around as long as that activation energy is not present. But once you get enough activation energy, those two molecules will speedily head downhill, releasing tremendous amounts of energy to the very stable water molecule. And we'll take a look at reaction progress diagrams later on. So expressing reaction rates, like anything else in chemistry, we need to be able to quantify or express a reaction rate. And the first thing you want to realize is that you're already familiar with rates. Rates are just changes per unit of time. So if you're driving in your car and you look down at your speedometer, your speedometer, you see a change in position per change in unit time. Perhaps you didn't think about it that way. So what's really happening here? What you're expressing is how far you travel in a single unit of time. It's typically, for us here in the States, miles per hour. If you're from pretty much anywhere else in the world, you probably express it in kilometers per hour. But that's just going to be the final position minus the initial position divided by the final time minus the initial time, and that will give you your average rate of speed. So for a reaction, we have a concentration of reactant A, and we have a concentration of our product B. And so all we're going to do is we're going to compare these two rates. So if we, for instance, are referencing just the formation of product, we'll have a reaction rate that says the change in concentration, typically brackets mean molarity, but it could be any unit of concentration, but it typically means molarity. And then divided by the change in time. We always express that as the final concentration at the end minus the initial concentration at the beginning, divided by the final time at the end minus the initial. Okay, I'll apologize. I'm having a few PowerPoint or Microsoft Office issues that I hope to get resolved, but let's see if we can't plow ahead. So as I was saying, rates of reaction with respect to chemical reactions are done in concentration, changes in concentration. That's what the little delta symbol means. In this case, we're measuring the change in the concentration of the product B in this very simple reaction divided by the change in time. And we express that as the concentration of B at time 2 minus the concentration of B at time 1. That's final concentration minus initial divided by final time minus initial time. Typical units will be in molarity per second. It could be different. You could see molarity per hour. You could see a concentration unit expressed differently than molarity. We may get to that. But then time in the bottom. And always remember that when you're expressing a rate, the unit of time in the denominator is 1 unit of that particular time. So this is molarity per 1 second. Okay? All right. So basic concepts. Here is a basic reaction. This is methanol plus hydrochloric acid, which is going to form chloromethane, and water. It's a simple 1-to-1-to-1-to-1 stoichiometry. So what we want to ask ourselves is what happens to the concentration of the reactants and products as the reaction proceeds? Well, reactants are consumed in a reaction as it proceeds in the forward direction. So the methanol concentration will go down and the hydrochloric acid concentration is going to go down. Meanwhile, the product concentrations, chloromethane and water, those concentrations will increase. And we can express that graphically and we can quantitate it numerically. So the rate of the reaction is defined as the change in the concentration per unit of time, and we could express it this way. Rate equals change in concentration per unit of time. If we want to express that rate with respect to the decrease in the concentration of methanol per unit of time, we would express it in this way. Okay, so here's our rate. We would express it as a negative value. Why negative? Because reactant concentrations go down. We say that reactants disappear over time. That is, the concentration goes down. The negative sign is simply an indication of the rate of disappearance. Now, if we take a look at the rates for all of these components in this simple 1 to 1 to 1 to 1 stoichiometry, we have a negative value for the methanol, which is a reactant, a negative value for the hydrochloric acid rate because it's a reactant, but a positive value for both of our products, chloromethane and water, because their concentrations are increasing. As a reaction proceeds, the concentration of the reactants decreases. That's why we give them a negative value, and the concentration of the products increases. That's why we give them a positive value. Now, that may be confusing to some folks, and it's completely understandable, because when we express the rate of a reaction, we never express, Okay, let's take one more look at the relationship between rates of reaction. So here we have a reaction that's moving in the forward direction, methanol reacting with HCl to form chloromethane and water. And we know that as the reaction moves forward in the forward direction, that the reactants are disappearing because they're getting used up. These two guys are getting used up to make our two products. So their concentration is going down. Now, the way that we calculate the change in concentration over time for any component of a reaction is we take the concentration at time 2, that is the final concentration for the period of time that we're measuring the rate, minus the initial concentration of that reactant or product. But let's just stick with reactants for the moment. And then we divide that by the change in time, which is time 2 minus time 1, so that's a change as well. Now, for reactants, because they disappear, we have a negative sign. But keep in mind, you have final concentration, which is a smaller number, minus the initial concentration, which is what you started with, which is going to be larger. So that gives you a negative value, and so what you wind up with is a negative times a negative, which gives you a positive value. And you never express reaction rates as negative values. You always express the overall rate as a positive value. It's not a problem with the products because the final concentration of product, because products up here, is going to be larger than the initial concentration. So T2 minus T1, that's always going to be a positive value. And the final concentration, a larger number minus a smaller concentration of your product, is going to be a positive value. So that will easily give you a positive rate for your reaction. But in any case, you always have express a reaction rate as a positive value, never as a negative value. Okay? Now let's take a look at one more aspect. Remember, for a reaction to take place, in this particular case, reactant A has to have a collision that's successful with reactant B to make the molecule product AB. So there has to be a collision that's involved. And the more reactant concentration that disappears, just imagine you've got trillions and trillions of these reactants and they're reacting and forming products. Now you have fewer and fewer of them in this space. The concentration is going down. Now they have a harder time finding each other. The probability of a successful collision goes down. We'll talk a little bit more about that when we talk about collision theory. And so what happens is all the rates slow down. the rate of disappearance of the reaction slows down, the rate of appearance of product slows down, which means that the overall rate of the reaction slows down. All right, I can't find my pen anymore, but that's okay. All right, so that brings us finally to this question. The rate of disappearance of a reactant, and here are your three choices. A decreases with time, B increases with time, C stays the same throughout the reaction. So I'm just going to leave that one to you. All right. Hopefully these problems will be cleared up by tomorrow and we can make some better videos. All right, bye-bye.